AOPS number theory 6.24. Find the smallest positive integer that is both a perfect power of 11 and is not a palindrome. So since 11 is symmetrical, that might be why it's a palindrome. So we expand the powers of x plus y. And we make x 10 and y equal to 1. So x plus y squared is equal to x squared plus 2xy plus y squared. So 11 squared, if x is 10 and y is 1, then 11 squared is 121. And then x plus y to the power of 3 is equal to x to the power of 3 plus 3x squared y plus 3xy squared plus y to the power of 3. So 11 to the power of 3 is equal to 1331, and that's when x is equal to 10 and y is equal to 1. And x plus y to the power of 4 is equal to x to the power of 4 plus 4x to the power of 3y plus 6x to the power of 2y to the power of 2 plus 4xy to the power of 3 plus y to the power of 4. So 11 to the power of 4 is equal to 14641 when x is 10 and y is 1. And these three are all palindromes, so then we keep testing. X plus y to the power of 5 is equal to x to the power of 5 plus 5x to the power of 4y plus 10x to the power of 3y to the power of 2 plus 10x to the power of 2y to the power of 3 plus 5xy to the power of 4 plus y to the power of 5. And if x is equal to 10 and y is equal to 1, then 11 to the power of 5 is 161051, which is not a palindrome. So the smallest positive integer that is not a palindrome and a perfect power of 11 is 161051. AOPS number theory 6.25. Find the largest integer n such that n has exactly 4 positive divisors and n divides factorial 100. So if it has exactly 4 positive divisors, then the prime factorization can be a to the power of 3 or b to the power of 1 times c to the power of 1. Because if it's a to the power of 3, the divisors are 1, a to the power of 1, a to the power of 2, and a to the power of 3. And if it's b to the power of 1 times c to the power of 1, the divisors are 1, b to the power of 1, c to the power of 1, and b to the power of 1 times c to the power of 1. So these are the only possible ways that there are 4 positive divisors. So if n is equal to a to the power of 3, then that means a to the power of 3 is divisible by factorial 100. So since we are looking for the largest prime a, then we are looking for the a that there are 3 multiples of a from 1 to 100. So that means 3a is less or equal to 100. So a is less or equal to 33, and the largest possible value of a that is prime is 31. So the largest is 31. So n would be 31 to the power of 3, since n is equal to a to the power of 3. So then that's the largest value of n. And if n is equal to the second case, b to the power of 1 times c to the power of 1, then we are looking for the largest primes b and c that are less than 100. So the two largest primes that are less than 100 are 89 and 97. So the largest possible value of n is equal to 89 times 97. So if we compare the two cases, we find the bigger one. So 89 times 97 is equal to 8,633, and 31 to the power of 3 is equal to 29,791, and 29,791 is greater than 8,633, so 29,791 is the greatest. AOPS number theory 6.26. In how many zeros does the decimal expansion of 100 to the power of 100 minus factorial 100 end? So 100 to the power of 100 is 100 to the power of 100 is equal to 10 to the power of 2 to the power of 100, which is equal to 10 to the power of 200. So that since it's 10 to the power of 200, that means it has 201 digits, because it's a 1 followed by 200 0. So that means 100 to the power of 100 has 201 digits. So now we count the number of zeros which 100 factorial 100 terminates. So since there are more powers of 2 than powers of 5 in the prime factorization, we to count the powers of 10, we need to find the number of powers of 5, because a power of 2 times a power of 5 makes a 0, makes a terminal 0. So 100 divided by 5 is equal to 20, and 20 divided by 5 is equal to 4. So there are 20 multiples of 5 from 1 to 100, and 4 of those are multiples of 5 squared. So 20 multiples of 5 and 4 multiples of 5 squared. And like 4 of these are multiples of 5 squared. So in total, there is 20 plus 4, which is 24 terminating zeros. So then we subtract, when we subtract these two, then both integers are multiples of 10 to the power of 24. So both are multiples of 10 to the power of 24. But the first one, this one, is a multiple of 24. And this one is a multiple of 10 to the power of 25. So that means the difference is a multiple is 10 to the power of 24 when we subtract it. So it will leave a positive remainder when you divide it by 10 to the power of 25. So it ends with exactly 24 terminating zeros. So the answer is 24.